Okay, hello everyone. Today I'm going to present to you incremental quantum measurement anomaly detection. I work with my colleagues Los Carbusos and Fabio Gonzalez, and we come from the National University of Colombia. So let me first introduce. Okay, let me introduce a little of the background. Our method is framed in the intersection of machine learning, statistics, and anomaly detection. There are very well-known methods that cause kernel density estimation, and also neural density estimation that are novel methods as the ones that I am going to present to you. Anomaly detection, as mentioned before, is an observation that deviates considerably from one concept of normality. It is also known as outlier detection or novelty detection. There are also other kinds of names. It can solve using a supervised approach, an unsupervised approach, or a semi-supervised approach. And there are several applications like medical anomaly detection, fraud detection, video surveillance, time series, induced anomaly detection, among others. Also, you can see that there are different kinds of anomalies. You can have point anomalies, group anomalies, contextual point anomalies, and also group contextual point anomalies. But with novel deep learning approaches, you can also capture more semantic anomalies like low texture anomaly or high level semantic anomalies. Then we can solve anomaly detection using a supervised approach. Yeah, you classify each point as a normal point or a normal point, but the problem is that in general we don't have enough abnormal points, so you need to take another approach that is a supervised learning approach. It's the general way in this case. So the problem statement with streaming and incremental learning is that the data arrives continuously, so it's impossible to store every data point, and it's infeasible in this case. Also, anomalies are few and scarce, so it's really difficult to learn the patterns that are inside the model, and the pattern on data change over time, so therefore it's really difficult to get the normality of each data point. And because of the constantly updated, you need to constantly update your model to be able to capture the anomaly detection. And also the complexity of those models, maybe one-class support vector machines on others, are really high. Because of that, we need to change a little bit the classical methods with incremental learning. In the literature, there are several streaming anomaly detection methods. They start with this work that is Storm from 2007, and there are several ones that are based on probabilistic, distance-based, or ensembles more related with random forests or isolated forests. Also, there are novel methods in deep learning approaches that combine maybe autoencoders or combine some kind of memory-based algorithm with an union of anomaly detection method. Therefore, our method is based more in the probabilistic way. I am going to introduce to you our method. So firstly, we have okay, I need to move a little bit this. So you can see this is the time series data where we can capture the density estimation of each point. What happens when what happened when the anomaly detection occurs? Okay, the density estimation is a method that for the anomaly points, their density is very low, so you can classify a normal data point as those points that has fewer or lower density estimation number. Sorry, wait a second, please. Okay. So, for that reason, I am going to define the density estimation. Density estimation is we have a probability density function, and we want to estimate that underlying probability function given data points. So there are maybe two approaches. One of them is parametric approaches, and the other is non-parametric approaches. Our method is based on non-parametric approach that is called kernel density estimation. Kernel density estimation is a non-parametric density estimation method. It also doesn't make any particular assumption about the underlying density function, and it's an unbiased estimator of the PDF. We can prove that. And once the PDF has been estimated, we can use that density estimation to provide a classification between normal and abnormal data points. As you can see here, this is a kernel density estimation with different kinds of kernels. And if you don't know how kernel density estimation works, it provides a kernel function in each training data points. And it's a memory-based algorithm, so in the training you don't optimize anything, you only store each point, similar to k-nearest neighborhood, and at the end you will compute a mean, the probability of a new point given the training data points. So you can compute the kernel between each training data point with the point that you want to estimate the density estimation. The most general or most used kernel in this approach is the Gaussian kernel. Is the one that we will use for our method. So, but there are several problems with kernel density estimation. One of them is that it is an inefficient memory-based algorithm, so the complexity is very high. Also, it can work with high-dimensional data because of the course of dimensionality, and with novel deep learning approaches is also not differentiable, so it cannot be easily integrable with novel deep learning approaches. So the training phase, the time complexity in kernel density estimation is 0.1, but the problem is that in the testing phase, the time is O and N, where the N is the number of training data points. So the complexity, if you have maybe 1 million training data points, it will increase heavily. And in the incremental approach, that you know that the number of points are big enough, so it's impossible to calculate the kernel density estimation in the incremental learning. So the problem statement is how kernel density estimation can be adapted in such a way that it can perform efficient anomaly detection on streaming data. I will show our method how to do that. So our method calls density matrices kernel density estimation. Is based on an early work that is called kernel density matrices kernel density estimation. It's an efficient approximation version of kernel density estimation. It's a non-memory based algorithm. Is differentiable, so we can combine with other deep learning approaches. Also, we have two ways of training. One of them is optimization free, but we can also optimize using a stochastic gradient descent. In our case, for the incremental learning approach, we only use the optimization free. Right now, I will explain this idea. It's based on two main ideas. That is random Fourier-feature to approximate the Gaussian kernel, and also density matrices to represent the probability of the probability of the model. So I am to introduce you our novel method that calls InQMAD, that is an incremental quantum measurement and anomaly detection. There are some parts of the method. The first part is this one. It's an adaptive Fourier-feature. If you don't know this word is for Rahimi et al. It's a word from 2007, and it wins in the Neolith in 2017 it's like an award for the most prominent word in the last 10 years of Neolith. And the idea is that we can represent a feature map of each point and avoid the calculation of the kernel, and we can estimate the Hilbert space in an approximation way. The other part, after we can compute the adaptive random Fourier-feature, we can start to provide a density matrix estimation. I will show you next the equations. The second part is a quantum measurement, so we can compute the density estimation for each point after we can calculate the density matrices. The density matrices, I will explain you a little bit of this. That is a quantum formalism that captures the classical and quantum probability of a given system. So after you can calculate the density estimation of each point, you can classify each point as a normal data point or a normal data point. If this is calculated as a normal data point, we can update our density matrices with this point, and with this approach, we can incrementally modify and update our density matrices. So this is our all of the phases. There are 4 phases. I will explain each one in more detail. So the first part, as I told you, is the map, the original data to a feature space using the random Fourier-feature. The second part is the initialization of the density matrices. The third phase is estimate the density of the new data points using density matrices and use the estimation to classify normal and abnormal data points. And the last part is the how to update the density matrices with information of the new data points. So the first phase, that is the data mapping, is a feature space approximation. We use the work of Rahimi et al. So the idea is that we can compute the kernel using only the dot product, an explicit dot product, avoid the calculation of the kernel. And using this information, we can modify a little bit the kernel density estimation. Also, the embedding here is also, it depends only on the W and the B parameters that are sampled from a normal distribution, and B is a uniform distribution. If you want more detail of how to calculate random Fourier-feature, you can see our work. Also, we modify a little bit the random Fourier-feature, and we call that adaptive Fourier-feature. That is a process where we can further turn this explicit map of the random Fourier-feature using neural networks, and using this approach, we can further turn each parameter. The second phase is the density matrix initialization. For this approach, we just only use a part of the increment of the initial training data points. We select some part of the initial string, and after that, we can calculate the density matrices using, as you can see, the explicit mapping of the random Fourier-feature. Using this, we can, we only train the density matrices using only normal data points. because we want to capture the density of the normal data points and not the abnormal data points. So we use an initial portion of the string for update the density matrices. Okay, as I told you, in quantum mechanics, the density matrices can capture the classic and quantum probability, and we use in our method as a way to capture that explicit density matrices. And the thing is that we can use only linear algebra operations to compute the density estimation. That is a really clever one. Also, we only use normal data points. The third phase is the density estimation. So when one novel data training testing data points arrive to the method, we need to calculate the density estimation of that point, and using that we can estimate an optimization. Okay, here we can compute with the initial data points, we compute a theta, as you can see here, a tau, that is used to classify each point. We use the initial data points to obtain that theta that represents, maybe we can just use, for instance, the density estimation and use a percentage, maybe the 2.5% of the data points that have lower values of the density. So using those data points, we can calculate the tau. So say if a new data testing point has is greater than that tau, we classify that point as normal, and in other cases we can classify that point as an anomaly. So at the end, we have a model that uses density matrices, that use random Fourier-features, and provides a density estimation, and we can classify normal and abnormal data points. The fourth phase, and the most important one, is how to update the density matrices. So the density matrices, when a novel point arrives and it is classified as an abnormal data point, we can join to the density matrices using this approach. And I will show you, this is an exponential average, similar to the one that are used in time series, but in this case we are using only the density matrices. We don't use any finance term here. And the update of the density matrices is used to estimate the density of the next sample in the data stream. So as you can see here, our method is like the red one. So those points that are with the points that are newer has greater importance for our method, and those points that are far away so has lower importance. So in this case, we can learn as an incremental approach. We imagine other methods that maybe, and we are maybe trying to get a novel method that can be captured maybe more far distance of the time series, but here we are just using the exponential method. The experimental setup for our method, we compare our method with 12 streaming data sets. Also, we test to 12 different methods of the state of the art. We perform also parameter research for all of the methods. We test, in our case, we test the learning rate, the adaptive Fourier-feature, the variance of the Gaussian kernel, and all the methods are compared using IUC ROC, that is the normal way to compare our methods in the state of the art. It's the normal method that is used in the state of the art.
Therefore, we test our InQMAD method in several datasets, and we compare them against several incremental learning algorithms, and we show that our method outperforms other state-of-the-art methods. Also, we use a Friedman test. So the conclusion is that InQMAD shows better performance than state-of-the-art algorithms. It computes density estimation as an incremental measurement, and our method shows better results than state-of-the-art.